Okay, so now that we have learned about horizontal launch projectile, we're going to learn about the when projectiles are shot at with an angle. Okay, so when they're projectile, when we have an angled launch, a projectile is launched with a velocity of v0. That's the initial velocity, and it's shot at an angle. So we're going to analyze the two motions for this, like we did the horizontal launch. So the horizontal launch, or horizontal motion rather, the speed remains constant, just like the speed of the horizontal launched. The horizontal speed remains the same, so it does not have any acceleration, and it doesn't change. So we write that as the acceleration in the x direction equals 0, and the velocity in the x direction is constant. But because we're now at an angle, the x velocity is equal to the component, which is the initial velocity times the cosine of the angle of launch, theta. So we're going to have to calculate this x velocity this time. The x is still called the range, just like it was before, and we use a formula for the range is the x velocity times time. So if we take this initial velocity of the projectile times the cosine of the angle of launch, we can put that together so we can calculate the range of the projectile. Okay, so that's a horizontal motion. It's basically the same as the horizontal launch, except that we have this angle going on now. So now we'll look at the vertical motion of the angled launch. So when an object is projected up, it goes up and it comes back down. So in the vertical motion, we have a decreasing speed first, and then an increasing speed in the second half. It's decelerated as it goes up, and then accelerated by gravity as it comes back down. So we have a component, the vertical component in the y direction is equal to the initial speed, or the initial velocity of the projectile, times the sine of the angle, because it's the vertical component. All of these formulas still are the same as for a horizontal launch. We will use this one mostly to find the height, maximum height. We'll be using that, but as you'll see in one of the examples, we're actually going to use this this third velocity, third formula to find the height. Now, the interesting thing about if we launch a projectile and it goes from one level to the same, or the same height, then the time up is equal to time down. We'll see how that works. All right, let's look at the trajectory. So this VO would be the initial velocity that's given at this angle. Here are the two components. Sometimes this vertical component is put on the end of the horizontal component, but as you well know, that it's also over here. So we have the initial velocity in the y direction, initial velocity in the x direction. And note that this velocity remains the same throughout. That it does not change. Vx is just equal to the same component all the way through. And then the y velocity is the greatest at the beginning. It then slows down. It then is 0 at the highest point, and then it increases so that those two speeds are the same, but that one's up and that one's down. And then this speed would be the same as the initial right there. And then this ending velocity would be equal to the initial velocity because we're adding the two together. Time up, because the displacement is the same at the beginning and the end, then the time up is equal to time down. Okay, our first example is a soccer ball that's kicked at 20 meters per second at 37 degrees, and we want to figure out how many seconds until it hits the ground. So let's set up a diagram. We have a 37 degree angle from the horizontal, and it goes at 20 meters per second. The soccer ball's trajectory is a parabola, and so we're going to figure out how much time it takes. So the tricky thing on this is we're going to use this the first equation, the change in velocity or change in displacement overall the entire time, interesting enough, is actually 0. So we're going to use 0 as a change in vertical displacement because it, compared to where it starts to where it ends, there is no change in height, change in displacement. But we're going to need the vertical component, and we get that because of because this is opposite. We take the initial velocity times the sine of the angle, so that is 20 sine 37. T is the unknown that we're looking for, and 1/2 of negative 9.8 t squared. So we simplify this a little bit. 20 sine 37 degrees is equal to 12, and 1/2 of 9.8 is 4.9. So we do have a quadratic, but because this is 0, then we can divide every term by t. So 0 divided by t, 12t divided by t, and 4.9 t squared divided by t simplifies by taking out one of the time, the t variables. We move the 12 over and divide by 4.9. The 12 comes over as negative. We divide that by negative 4.9 so that our time is going to be positive, and that comes out to 2.45 seconds. So that's how long it takes for the soccer ball to be launched and then hit the ground. 2.45 seconds at that velocity, at that angle. Well, the next question to be asked is how far does it go? So what we're asking now is what the range is. So we use the formula that we just made for range, and so this is equal to the x velocity times the time of flight. The x velocity is a component of the initial velocity, and remember that doesn't change, so we're going to replace that vx with initial velocity times the cosine of the angle, and so then we plug in the values. So it's 20 cosine 37 times the time we just calculated of 2.45. Put that in your calculator, and it comes out to 39 meters. So it's 39 meter range. Next question is, how high does it go? So now we can use the same formula, but now instead of using the total time, and since it's landing at the same displacement that it was launched, the time up is half of the time that we calculated. And so that comes out to 1.23 seconds, and we can use now to calculate the change in vertical displacement by putting in the values of, once again, the initial vertical velocity is 20 sine 37, just like it was before from that component, times half of the time, 1.23, and then plus 1/2, negative 9.8. It's very critical that that negative is used. Before it was, we could sometimes ignore the negative, but because this is going up and this acceleration is downward, we have to be sure that negative 9.8 shows up. And then t squared using half the time, 1.25. You put all of that in your calculator and hit the enter one time, and it comes out to 4.6 meters. So just make a note on that when you're calculating the initially, we use 0 as a vertical displacement because it lands the same height as it is launched. And then when we're doing the maximum height, we're only using half the time. Okay, so here's our next example. We have a clown on a 125 meter platform and is shot at 105 meters per second at an angle of 20 degrees up. What is the time of flight, maximum height, and the range? So let's set this problem up. So we have this platform that's 125 meters up, and we're going to shoot this clown into the safety pool down there. So it's launched at 105 meters per second at 20 degrees up from the horizontal, and his trajectory puts him right in the middle of the nice safe pool. All right, so we're going to use the first equation that we used last time to find the time of flight. In order to do that, though, we need to have the initial velocity in the y, so it's going to be a component of the initial velocity given. So we're going to calculate that and place it in here. Now, like the last problem, the change in y is not going to be 0 because it's starting out at 125 meters up. So we're going to put that in, that the change in displacement in the y direction will be negative 125. Here's the component, 105 times the sine of 20 degrees times time, plus 1/2 of negative 9.8 t squared. Be sure that if it's starting here, it's going to go down 125, so that's negative, and the acceleration is negative. And this is in an upward direction because it's a component. Okay, so we're going to calculate that and rearrange it. So 105 sine 20 comes out to 36. We're going to move that over with the 125, so we subtract that, and then 1/2 of negative 9.8 is 4.9, and we're going to move that over as a positive. I always find that when we get a quadratic, it's easier if the leading coefficient is a positive. It's just a habit of mine that I use. Now, how are we going to solve a quadratic for the roots? There are a couple ways. One would be factoring. Well, it doesn't look like it's a nice thing to factor, so we're not going to use that. So we're going to jump first right to the quadratic equation, where b is negative 36, and b squared, which I could just leave out the negative when I square it, minus 4a, which is 4.9, times c, which is negative 125, all divided by 4, or 2 times a, which is 4.9. So I'm going to calculate that, put all that in my calculator, and it comes out to, you can pause this video while you calculate it, comes out to 9.92 seconds. The other answer is if you use a subtract 36 minus this square root, then it comes out to negative 2.6 seconds, which is redundant for physicists to get. Another way to do that is to take that quadratic, put it in your graphing calculator, and end up with finding the roots. Let's take a look at what that would look like in your graphing calculator. I did this previously, so it looks like this. It has a y-intercept of negative 125, and then the two roots are here and here. Your graphing calculator will, you can use the second calc function to find the zeros, and then you can find this at 9.919, which I round to 9.92. So that's a method of doing that. So maybe you'll find that interesting. If you want to learn more about how to do that, then Google it or ask me. Okay, so we have 9.92, which is the time of flight. We're going to find the maximum height now. Well, the maximum height it goes from the bottom here all the way to the top. So I'm going to choose to use this formula because the interesting thing is when it gets to the maximum height, the velocity in the y direction is 0. So that's going to go into here, making that 0. And then I'm going to calculate delta y, which is going to be the distance above the platform that it goes. So I put in 0 here. I get the component in the y direction, again, same as I used in the first part, 105 sine 20. Don't forget to square that, plus 2 times negative 9.8. And then I'm going to solve my equation for delta y. So I'm going to multiply this, square it, move that over to the other side of the equation, and then divide by 2 times 9.8. And that comes out to 1290 after you square it. And then this is 19.6. That value, the change in y above the platform is 66 meters. And then I add that to 125, and that comes out to a total of 191 meters from the maximum height. Okay, so the last part is to find the range. The range goes from the edge of the platform to the middle of the safety pool. So to find that, I'm going to use the same formula I've used for the range. The only trick is that Vx, I'm going to use the component, which is using the cosine times the initial velocity, cosine of 20 degrees. So I'm going to place that in place of Vx. That 105 cosine of 20 times the total time of flight, which is 9.92 that I obtained from part 1. Put all that in my calculator, and I get 979 meters. So the clown safely lands in the middle of the pool with that initial velocity at that angle. Okay, so it's a little tricky. You got to be careful and use the components that we learned how to calculate. In this case, we use 3 different formulas and all. Okay, well, that's it. So thanks for watching.